So in the last class, we are discussing about this coherence of a beam, how it is defined. So we have, so when we talk about any source, which basically we have a electromagnetic wave that is associated with the wave or the incident light, and this electromagnetic wave is represented by a electric field and magnetic field. So normally, when we express the propagation of the wave, so we say the electric field is actually there is an oscillating electric field, which is given by in a one-dimensional form, which is given by this. Uh, now, so this is like a sinusoidal wave, which is always not sinusoidal when you look at the wave train for in some duration of time. So now we would expect that the electromagnetic wave, if it is coherent, it should be always follows this behavior, let's say the amplitude as a function of time. However, there is always some, so due to the process, how the electromagnetic wave is generated, so that leads to a finite time over which this electric field is, behaves like a coherent source, or it behaves like a sinusoidal wave. So many times you will observe that your propagating wave, the electric field, when you plot it as a function of time, so it can have some, let's say, tiny jump here. That means the phase relation is lost. Okay. And then again, you have a constant phase relation from one point to another point, and then again, maybe there is a change, and so this duration for which you have a constant phase relation in the amplitude as a function of time. So this time is known as the coherence time of the wave. Okay, so this is the coherence time, and the length, so this would correspond to certain length of your wave. So that length, this is your tau c, and the coherence length L will be given by tau c into c. Now this has consequence when you do perform a interference experiment, because now if I perform a double slit experiment, and this is my source S1, this is source S2, and this is the T which I have defined. Now if I look at this point P, where I want to know, this is the point where I want to obtain what is the interference fringe, what is the fringe pattern here. So in that way, I have to calculate the path difference, that is our S1P minus S2P, or whatever, S2P minus S1P, that is the path difference you have to calculate. And now if this path difference is, let's say we call this delta, is greater than this coherence length, so that means the wave train that arrives from S1 at point P is let's say sinusoidal, but the wave train that arrives from S2 at point P has a different phase, completely different phase compared to the wave coming from S1. So that means there is so there is no phase relation between the wave that comes from S1 and S2, and that will actually lead to a no interference. So in that case, there will be no interference. So this is essential because all the light sources that you use always have some finite coherence time or coherence length. So sometimes this coherence, this kind of coherence is known as also longitudinal coherence. So to have to obtain an interference fringe, even if you say it is a coherent monochromatic wave, so still your the path difference that you have at the point P should be less than this coherence length. Okay. Otherwise, there will be no interference. So normally, if you take a laser, so this coherence length is quite high, about 15 meter. Okay, so that is the and that in terms of the phase or the time coherence time is about 50 nanoseconds. This also can be understood in a Michelson interferometer. So similarly, you will have like in the Michelson interferometer, the distance between the mirror D should be of the order of should be less than this coherence length L. So so this has a consequence in terms of you can define how monochromatic your incoming source is. So if you know what is the coherence length or the coherence time, so you can say what is the purity or how monochromatic the wave. So if you know this coherence time, so now we can look at again this double slit experiment again to understand that. So let's say if you have a situation, again we have this. So we are expecting a interference pattern on the screen here. Now we have, let's say, two wavelengths. So let's say, for example, you use the sodium light. So you have D1 and D2 sodium, the wavelength. And so you have basically in that case, so let's say we use a sodium source. So where you have two wavelengths, lambda 1 and lambda 2. So each one will satisfy the condition for the interference. And in that case, let's say the first one would be, let's say 2D is equal to m lambda 1. And the other one will be equal to m lambda 2. Okay, so or let's say n lambda 2. So anyway, both are integers, m and n would be integers. Now, let's say for certain situation, it may happen that your second, this condition would be, let's say, in a situation where you have 2D is equal to m plus half lambda 2. Okay, so the first condition is, so the separation is such that, so for lambda 1, it satisfies this condition, and for lambda 2, this is the condition that is for the interference that is satisfied. So if you subtract these two, so what you have is 2d by lambda 2 minus 2d by lambda 1 will be equal to half. And this actually would mean, so this is corresponds to a maxima, this corresponds to a minima. So if this is the situation, in that case, what would happen? So your minima of one, so interference fringe corresponding to one wavelength will fall on the maxima of the other. So basically, you will have no interference. So if this is the situation, so there is no interference fringes will be observed, or the interference pattern will be very, the contrast will be low. So because there is a superposition, not superposition here, but there is one maxima falling on the another minima, so there will be, the contrast will be very poor. And this actually, so if you simplify this relation, so what we would get is 2D would be equal to lambda 1 lambda 2 by 2 lambda 1 minus lambda 2. Okay, so this is what this condition means. If you have two discrete wavelengths, so this is the condition when you would observe no interference fringes even if they are the coherent beam. And normally when we look at sources, so this is, let's say, for a particular example of sodium light, but most of the sources have actually defined in such a way that you have a spread of wavelength. So you have a lambda, and your wavelength has a spread of delta lambda. So most of the incoming electromagnetic wave will have a, so some can have a wavelength lambda, some can have lambda plus half of delta lambda, or half lambda plus delta lambda. So this is a continuous spread in the wavelength of the incoming wave. So that is typically that happens for laser, for example, if you are using laser. So this relation also can be extended to this normal sources where you have a spread of wavelength. So in that case, you would write this relation. So 2D, you can write something like lambda square by delta lambda. So if this is the condition for your incoming wave, where the wave has a certain spread in wavelength, so then you would observe no interference pattern. So that means your so this delta lambda is basically defines your monochromaticity of the wave. So that means if you say your delta lambda is really narrow, very small, so that means it is really monochromatic, because normally in any source it is always like that, there will be some spread in the wavelength. And what you would like to have is that this wavelength spread is as narrow as possible. So that means the wave is really highly monochromatic. So now if the spread is too large, so that would mean that this condition will be fulfilled, and in that case there will be no interference. Even if you have, so this is basically your, it will become almost like an incoherent beam. So so this D that we are talking about, D is basically what, the distance between the slits. Okay, and what we saw earlier, that this D should be of the order of or this 2D should be of the order of your L, which is your coherence length. So if it is more than that, so then there will be also no interference fringes. Okay, that means, yes.
Sir, what is the physical means of coherent length?
Yeah, so coherent length we saw no here. This is, let's say if I have a wave, so I say I have an incoming wave where I am plotting the amplitude of electric field, so it oscillates like a cosine function here as a function of time. So this is like for all duration of time t. So like if I say my time is between infinity minus infinity to plus infinity, between that time, it is always would be like this. This is an ideal case, but in a practical situation, due to the process how the electromagnetic wave is generated, so this condition is not true for entire duration of time. So this condition will be true only for, let's say, when so if you look at the variation of electric field as a function of time over from over a large period of time, so you will see some fluctuation, some points where you will see some deviation of the electric field, how it oscillates as a function of time. So it will not follow your cosine function. Okay, so this duration for which this delta t, let's say tau, for this duration, the wave is actually looks like a cosine wave. Now, with it has certain phase phi, let's say. Now, if there is some disturbance or some deviation happens, so there will be this kind of wave you will observe for a moment, and then again you will have another wave train, which is again will be a cosine function, but with a different phase. Okay, so the phase is now different, and that's why so you can have uh, you can say E is equal to E naught. So let's write it down again. So I can say E is equal to E naught cosine kx minus omega t plus phi 1, let's say, and another time. So this is, let's say, for time period delta t1, and now for another time. So this is again kx minus omega t plus phi 2. So this is delta t2. So for this period of time. So this is again, there is no phase relation between these two waves. Okay. Although within this period of delta t1, the wave is coherent, but now the wave after this tau c has a different phase phi 2. So this is what the physical meaning of that. Okay, so this is the temporal coherence we are talking about. Now, within this time period delta t1, the wave would travel certain distance, right? That distance is nothing but your velocity due into, so this is your uh, L1 L2 by c, so something like that. So this is for this length, that if you talk about what is the length over which this wave is coherent, has the same phase is this distance L1. So after that, again, the phase will be different. Okay, so this is what this coherence length means.
Yes, sir. Thank you,
Yeah.
sir.
Okay. Yes. Another question, Jatin?
Yes, sir. I have a doubt in the Michelson interferometry. So
Okay. Okay.
what you taught
Hmm.
in the class was that the part difference 2d cos theta is m lambda, that is constructive. But
Hmm.
in the book, I found that m lambda is destructive.
2D sine theta equal to m
2d cos
lambda.
theta, sir.
2D cos theta. Okay.
Yes, sir. In the class, you taught that m lambda is constructive, but on reading the book, I found that m lambda is destructive.
Uh, okay. So see that. So maybe we'll discuss that in after the class. Okay, or maybe sometime later. Hmm?
Okay, sir.
Okay. Uh, so this is about the coherence length. Uh, Let me just check that. What is that?
So I can share the screen. I am ready with the page.
Let me just open that from here. No, I think in the book you say m lambda corresponds to destructive
In the
interference.
yes, sir, in the book
2D,
destructive for m lambda.
uh, I am not sure. I mean, I have still the same 2D cosine theta m lambda means constructive, and when it is m plus half lambda, it is destructive.
In the books,
So
in
you
the Michelson interferometry, I found that.
okay? So you can share that maybe screenshot of that page. Send it to me. I will have a look. Hmm?
Okay, sir.
So it is from the sixth edition of the book.
Yes, sir.
Okay. So maybe there is. So I will check with my one. So I am actually I have a the book. I mean not the PDF copy. So it will be difficult to say what is the. So I have to check the PDF copy. So I don't have the PDF copy of that book. So I have a book like so that is what I'm following. But in the book it is written it is m lambda should be constructive. So you can send that screenshot of that page or maybe that chapter. I will have a look. Hmm?
Okay, sir.
Okay.
Sorry, even my book shows m lambda as destructive.
Okay. Okay. So maybe there is a problem with that edition. So you can send me that part. I will check and then clarify. Hmm? Okay.
Yes, sir.
Okay. Okay. So this is sorry. So this is the coherence length or the so how this coherence would lead to a or define the monochromaticity. That is what we were talking about. So now this lambda square by delta lambda is a bit difficult to comprehend it. So what we normally is done is that you express it in terms of rather frequency. So not lambda, but in terms of frequencies. So what is the frequency in that case? So frequency is given by c by lambda. So your frequency spread would be c by lambda square, ignoring the minus sign here. So this is what c a delta mu would be, and which should be equal to your uh, c by L. Okay, and that means your delta nu would be proportional to, or delta nu divided by nu would be equal to uh, so delta lambda by lambda square is L, yeah. So delta nu by nu or delta nu itself only, so it is proportional to 1 by L, which is nothing but will be proportional to 1 by tau c. So that means this frequency spread is inversely proportional to your temporal coherence or the coherence time of the wave. So if you want to minimize or make this frequency spread as much as possible, that means if you want to make it more monochromatic, so tau c, tau should be large. So this is obvious. So if my wave train remains coherent for a longer period of time, so that means the monochromaticity is better. So this is known as a, so you can define the spectral purity or monochromaticity using this. So there is another coherence actually also we discussed when we talk about coherent sources, that is known as the spatial coherence. So the first one is the temporal coherence or longitudinal coherence. So this is known as spatial coherence or sometimes also known as lateral coherence. So the earlier one was based on basically what is the describes the monochromatic nature of the light, how monochromatic it is. And this one talks about when, so if you have an extended source, okay, so what is the relation, the phase relation when a wave comes from one point of that source compared to another point. So let's say, to give an example to appreciate that, so let's say again, you look at the double slit experiment. Now I have, let's say, a source here S, another source S prime exactly here on the same place. So S and S prime, so both sitting at the same point. Okay. Now, if I they have, let's say, they are both monochromatic, so same wavelength. Now, if I want to see the interference pattern, so I will observe this interference pattern because I mean, both will have the exactly matching interference pattern. So the interference pattern due to S and S prime will match exactly because they're at the same position. So now let's say I change or move this S prime a little bit, shift this S prime a little bit. So now I have a situation, let's say my S prime is somewhere here, okay, and this distance is, let's say, L. Now, so in order to satisfy or to find out the condition for your interference fringes, so again you have to calculate what is the uh, path difference. So if I want to calculate or know the fringe pattern at here, so I have to calculate what is the path difference between, again, the light waves or the waves coming from from S1 and S2 due to S prime and due to S. Both I have to take into account, right? So I will have a wave from S to S1 and S2. Also, I have a wave from S prime to S1 and S2, and both have to satisfy the condition for the interference fringes. Now, but due to this shifting, there is an additional path difference that has been introduced here compared to the source S. So only by shifting this source a little bit higher, so I have produced or introduced additional path difference, and that additional path difference is given by S prime S1 minus S prime S2, which is yeah, so this is the additional path difference I have introduced due to this by shifting the source by a distance L. So now if this additional path difference is equal to lambda by 2, so if I move S prime in such a way that this path difference is lambda by 2, so that means the interference, the fringe that produced due to S is not changing, right? So the due to S, let's say that path difference. So if I have S1 or sorry S1, this S1p minus S2p is integral multiple of lambda, so it is, let's say, maxima. So if I have a maxima due to S at point P, but due to the shifting S prime by lambda by 2, so I will have a minima due to S prime at, okay, and that means if this is the situation, then again I have although I have a coherent source, still I will not satisfy the interference condition, and I will have a very poor contrast or even no interference pattern. Okay, so this defines actually what should be the length or L, the value of L should be in order to get a interference pattern if you take an extended source. So you can use a simple geometry and calculate, find out this S prime S1 minus S prime S2 is of the order of L D by A. So what is A? A is this distance. Okay, and you assume this angle is about theta. Okay, so this angle, this if you take this angle to be theta, and for small theta you can find out that S prime S1 minus S prime S2 is equal to LD by A, and also you have to assume that A is much greater than D and L. So the source is much far away from the extension is much small, very compared to your distance from the uh, point from where this you get the interference, and or your real source and the virtual source. So if you have this condition, so then you will have no interference pattern for an extended source. Okay, and that means your L should be of the order of, or in fact less than this value, uh, in order to have a in order to observe an interference pattern uh, in this case. Okay, so this can be also simplified or even so this is like what we are considering about like two different points, so S and S prime. So if I have, instead of an extended source, like let's say I have geometry like this now, this is my source S prime. Okay, and now I want to observe what is the interference pattern due to that. So if this angle, so the source basically subtends an angle theta here. So this is your S2, this is your S1, and this is your D. So this is your A, and so this L is, so this is your L. That is the extension or the length of the extended source. So in that case, the fringe will disappear when L is equal to lambda, or what you would expect that if you take, let's say, lambda A by D, if the length of the source is lambda A by D, so in that case, for this point, so if I take a point here, then if I, there will be a corresponding point lambda A by 2D. Okay, so this will correspond to lambda lambda A by 2D. So this is, let's say, 0. So this point, the coordinate will be lambda A by 2D. So this point and this point will make sure that there is a the interference pattern is poor, the contrast is poor, or there will be no interference pattern. So for each point, so you will find another corresponding point at a distance lambda A by 2D. So which will make sure that there is no interference fringe. So that means the minimum size, or your the source size, should be actually less than lambda A by D, even much less than this. So this is what you would like to have if you want to see the interference pattern in this case, and which actually turns out to be what should be the relation between D and lambda. So in that case, you can write D would be equal to lambda A by L, and what is lambda A by L is, this is lambda by theta. So where theta is of the order of L by. Okay. So this the length L or sorry, so this D, this distance between your S1 and S2, so So this is the distance d. So it should be always of the order of this lambda by theta, which is known as the lateral coherence length. So it is different from the temporal one. So the temporal one defines the monochromatic nature. This lateral coherence length defines for an extended source, like if you have two different points, so whether the wave that is coming from that point is there, the phase is they are related or not. So both conditions need to be satisfied in order to have a interference pattern. So for example, if you take a sunlight, okay, so if you have a sun that let's say your that is the source where it falls at an angle 32 degrees. So in that case, and if you say lambda is about 5,000 angstrom, okay, so your lateral coherence length should be lambda by theta. So if you convert it into radian and then calculate, so it will be about 0.005 centimeter. So that means if the value of d should be less than 0.005 centimeter, so in that case you will observe a interference pattern when you have the sun, you are using sun as a source. If it is more than that, so then you will not observe any interference pattern. Okay. So this is about the coherence, the properties of a wave, which basically very useful in case of like when we talk about laser. So that's why laser is actually considered as the best source, coherent source, because you have large temporal coherence or longitudinal coherence and really large lateral coherence also. So the coherence, lateral coherence length or the spatial coherence also large. Okay? So you can use an extended source of laser and still the phase relation will be really strong. So this is why laser is used as a, if you want to use a coherent source, you want to make it use a laser. Okay. So next we will go to another topic now on diffraction. So I think diffraction also you, so any question from this section before we move forward? Okay, so it's not, so let's then go to a diffraction. So when we say diffraction, so this is, here I am showing an example of a diffraction pattern. So what you have is basically some aperture, okay, which is, in this case, it is a slit, let's say, not narrow slit, and you have basically parallel wave that that are incident on the slit. So it is a single slit that we are using, and then what you have is, so here they are using a lens to focus basically the light on the screen. So that's why this f basically is the focal length of the lens, and you will observe a pattern or a distribution of intensity on the screen due to this single slit. Okay, so what you have is yeah, so here I am showing some pictures using a, so this is again from the web, which shows when you vary the slit width, so how the diffraction pattern changes. So this is again from a single slit, so that's like the one shown here, and you can vary the width. And remember, so when we are looking at the diffraction pattern, we are looking at a distribution along the width. Okay, so it is not in the length, along the length of the slit. So the distribution is not in this direction, but the distribution is actually, the intensity distribution is along this direction. So that is the diffraction pattern that you are seeing. So this phenomenon of this distribution of a light wave due to a single aperture, it can be a slit, it can be, so the geometry can be this, like a slit or like a pinhole or any kind of aperture. When the light passes through that, you will observe this kind of distribution of intensity, and that is what the diffraction is. That is known as diffraction. So there are two different diffraction. There are two categories actually. So one is the Fraunhofer, and the other is the Fresnel type diffraction. So we will focus on the Fraunhofer diffraction today. And what is Fraunhofer diffraction? So what you have is you would, in this Fraunhofer diffraction, so you have a slit where you have a incident like parallel light incident on the slit, and that means you assume that the source is at infinite. The source, let's say, is at a distance, so infinite distance. So similarly, you would assume your screen should be also at a infinite distance from the from your aperture. So in that case, you will observe the diffraction pattern on your screen. And how do you make that? So normally, if you have a finite source or a source at a finite distance, so you would put a lens which will so you will put a lens in such a way. So you would put a lens here, and you put the source at the focal length of this lens. So you have a parallel beam, and you assume, so that makes sure that your source is like at infinity. And then when you look at the screen, so you will also put another lens. So that's why you will see a it will be like make sure that your screen is somehow far away or infinite at infinite distance from the slit. So you have basically what you have, a slit with certain width, let's say B. So this slit width is B, and then you observe this diffraction pattern. So I think maybe I have another picture here. So we'll go back to that picture. Oh yeah, yes, I have. Oh no. Okay, I already saw that. Okay. So this is what the, but when you look closely, when we will go into the theory of this diffraction, you will see that there is not really a big difference between diffraction and interference. Okay. So although they are very distinct optical phenomena, but at a fundamental level, there is not a big difference. So it is really hard to say what is a real difference between an interference and diffraction. Okay, so if you want to look at the theory of diffraction and to understand how what is the intensity distribution and what is the condition that you will observe this kind of maxima and minima, so we'll go to a simple method here. So what we have is, let's say we assume, so this is a single slit, but you assume, let's say this is your one point which gives rise to your, so you basically divide each your slit into small points, which and each point now behaves like a source of a electromagnetic wave. So you divide your single slit into many tiny point sources, S1, S2, S3, and so on. And then you say the distance between these two sources would be, let's say, delta. Okay, so this is the distance. And then first you will calculate what is the path difference when the light goes from S1 and S2. Okay, and then we will extend it, and you will find a theory of diffraction. So let's look at these two sources, S1 and S2. So let me draw it again. So you have S1 and S2. Here you have, this is delta, and you have a let's say ray going like this. Okay, but you will have a path length, extra path length between S1 and S2, uh, given by, so if this angle is theta. Okay, so let's say we assume, so this is the 90 degrees, so this is theta. So in that case, your path difference here, so let's say this, or maybe I'll draw a better one. So you have something like this. So let's say take this point. So I have something like this, and this is another point, which will basically now this S1, S2, S3, they will interfere. Okay, and the path length would be, so this is S1, this is S2, so this is, let's say, S prime, and this angle is, let's say, theta. Okay, and so this S2 S prime is the additional path difference, which is nothing but delta sine theta. Okay, so this is the extra path length that the ray would travel when it goes from S1, or the ray that goes from S2 compared to S1. And the phase difference would correspond to, so 2 pi by lambda into delta sine theta. That is the phase difference. So if you have a electric field which is given by a incoming electric field, the time dependence, let's say we say it is a cosine omega t. So from S1, then so this is E1, E2 would be, the phase difference would be cosine omega t minus pi. So there is a extra phase difference we have introduced. So this is from S2. So E3 would be a cosine omega t minus 2 pi, and so on. So what you would have is, so if you have like n sources, so En would be a cosine omega t minus n minus 1 pi. Okay. And now, in order to calculate the amplitude at point P on the screen, so you have to just add all the fields. So this is a superposition of all the electric field. So you will just add E1 plus E2 plus E3 up to En. And if you do that, so you will get basically A into cos omega t plus cos omega t minus phi, and cos omega t minus n minus 1 pi. This is the resultant field, electric field at a point on the screen, which you can actually solve it and write a simplified version of that, something like this. So this sum cos omega t plus cos omega t minus phi, so you can write it down in in a form. So let me just write it down. So half n minus 1 pi, where E naught is given by A sine n pi by 2 divided by sine pi by 2. So this is the amplitude of the resultant electric field, uh, and this is the phase part. So in order to observe or to explain the diffraction pattern, so we would say in this, when we say n should go to infinite, because we are dividing into very tiny, very small sources, n should go to infinite and delta should go to 0. Basically, they are really the separation between the this individual sources we are talking about in the slit. The distance is as small as possible. This is the limit in which we will calculate the diffraction pattern. But we should make sure that this n delta, the product, should be equal to b. Okay, so this is what the condition we would apply. And under this condition, so your what is n phi by 2? N phi by 2, like phi we calculated earlier. So we saw phi is 2 pi by lambda delta sine theta. So n phi by 2 is nothing but n by 2. So 2 pi by lambda into delta sine theta. Okay, which you can simplify. So n lambda, we say it is equal to b. So it will be pi by lambda into p sine theta. Or phi, now we can write it like 2 pi a by lambda b sine theta by n. So that is the phase difference. And the amplitude E0, we can also write it down like this: a sine n phi by 2 divided by a, so this is sine phi by 2, right? This is the one. So if in the situation when we say, so we have assumed that n goes to 0, sorry, infinite. So that means pi should go to 0. So if you apply that condition, your E0 would be equal to a sine n pi by 2, and sine pi by 2, you can say it is nothing but pi by 2 in the condition when pi goes to 0. So sine pi by 2 would be pi by 2. And if you now substitute the values of pi that we have calculated, so what we will get is n a sine pi by lambda p sine theta divided by pi by lambda b sine theta, which you would write your E naught would be equal to amplitude A to sine beta by beta. So here A is the amplitude n into A, and what is beta? Beta is pi b sine theta by lambda. Okay, so now what is the condition or what is the intensity? So the amplitude, we say it is not cosine omega t minus now beta, we are writing instead of pi, we will write it as minus beta, and E naught is defined by this. So this is your E naught, and this is your electric field. And the intensity will be this E square, so will be proportional to E square, so which is nothing but I naught sine square beta beta square. So when theta is equal to 0, Okay, so for the principal axis, or when there is the angle of incidence is theta is 0, so in that case this sine square beta by beta square would go to 0, sorry 1, and then your intensity is equal to Imax, which is known as your central maximum. That is the central maximum of the diffraction. So you can also differentiate this with respect to beta to find out the condition for maxima and minima. And if you do that, you will find out, so let's, if you do the differentiation, so you will find the condition for maxima and minima, which is given by sine beta into beta minus tan beta will be equal to 0. So for minima, your sine beta would be equal to 0. So this will correspond to, so one solution will correspond to a minima, and the maxima would correspond to beta is equal to tan beta. So sine beta is equal to 0 means beta is equal to m pi. That is the condition for minima, but m should not be equal to 0. Otherwise, so m is equal to 0 corresponds to the central maximum. So beta is equal to m pi corresponds to your minima, and beta equal to tan beta corresponds to your maxima. So you can solve it in a graphical way, and you can calculate what is the position of intensity and so on. So I'll skip that, and you can find out what is the intensity, the position of where you will observe maxima, and what is the value of intensity at those points. So now instead of taking a slit like before, so if you take a circular aperture, so if you take a situation where now you have, instead of a slit, you have a circular aperture, and this is your incident light. So what would you observe on the screen? So the diffraction pattern due to this will be more like a circular fringes, which are known as the airy pattern. Oh, sorry, this is, there it is, airy pattern on the screen. That is what you will obtain. So instead of going into that theory, so we'll just write the intensity distribution for an airy pattern, so which is given by this function J1V by V square. So similar to the earlier one, sine square beta by sine beta by beta whole square. So now instead of that, we have J1V by V. What is J1V? So J1V is known as the Bessel function of first order. So this is again a mathematical function very similar to your sine function, but with a different amplitude and different periodicity. Okay, so this is very similar to your sine function. And what is this V? V is again like earlier it was we defined for beta. So here we are saying it is V 2 pi by lambda A sine theta. Now here what is A? A is the radius of the aperture. Okay, so this is the radius of the aperture. So you, if you plot these functions, so if you are really familiar with MATLAB or any programming tool, so you can actually easily plot these functions. So if you want to explore that, so I would suggest you do that. So you can plot, for example, J1V. So this Bessel function is like a standard function that you can, so it is available in MATLAB. So you can, you don't have to write the whole function for yourself actually. So that is a good thing. So J1B by B, you can write that's the whole square, okay. And you can also plot if you want to see how that this varies. So sine x by x or sine x by x whole square. So instead of like J1B, I can say this is, let's say J1x. So x is your variable, and you can put maybe x varies from 0 to 10 pi or something like that. So you can try to plot in MATLAB if you are familiar with that, or any other programming language. You can plot that and see how this depends as a function of x. So you can plot a one-dimensional function and see how it varies, and what is the difference between your J1, this variation, uh, J1 x by, so this will be x again, J1 x by x whole square, sine x by x. So how they are different, so you can plot and understand that. So with this diffraction, there is always a associated something known as a angular divergence, which is known as delta theta, which is given by lambda divided by the dimension of aperture. So in case of, if I take a slit, so this angular divergence would be lambda by b. B is the width. And for this circular aperture, so delta theta would be equal to lambda by d, or 2a, where a is the radius of aperture. So this is the angular divergence that you would expect for any beam when it is getting diffracted. Okay, so now instead of taking one slit, so let's say we put, let's say, so do I have a figure? Yeah, okay. So let me put two slits and try to see what happens with respect to the diffraction. So now I have two slits similar to the double slit experiment, but now we are talking in terms of diffraction. So this is, we say this is both have the same width, slit width is the same. The distance is, we say d, okay. And we want to see what is the diffraction pattern, how it, what is the difference. So now you can say, you can assume that the first slit behaves like, so the diffraction pattern from slit A, let's say this is slit A, this is slit B. So this electric field from slit A would be given by A sine beta divided by beta. That is the amplitude of the electric field. And what is the amplitude of electric field from B? Again, it will be the same, sine beta divided by beta cos omega t minus beta. But there will be an additional phase difference. Okay, so because there are two different slits, so there will be additional phase difference from the electric field associated with the slit B. And what is that phase difference? Phase difference will be again similar to what we saw in the diffraction case, 2 pi by lambda d sine theta. That is the phase difference. So that is the phase difference between a source. So if you say any point on A will have a phase difference of 2 pi by lambda d sine theta with respect to any point in slit B. So now if we find the resultant electric field, so you will then do the superposition. So that is E1 plus E2. So if you add it and use a little bit of simple trigonometric relation, so what you will obtain finally is something 2a sine beta by beta cosine gamma cosine omega t minus beta minus phi 1 by Okay, so this is what you will obtain. So when you add up these two, or you take the superposition. And what is gamma? Gamma is, we have defined here as phi 1 by 2, which is, let's say, pi by lambda into d sine theta. So phi is 2 pi by lambda d sine theta. So gamma would be this much. And what is the intensity? So intensity will be your 4 I naught square sine square beta by beta square cos square gamma. Now you have one extra term compared to a single slit one. So this is a intensity due to the single slit. This is the intensity due to the diffraction interference of two slits. So this extra term appears due to the interference pattern that has between the two slits. So this sine square beta by beta square term is due to the diffraction pattern that comes from the single slit. Okay, and this shows how the diffraction and interference pattern is really closely related. So they're not that much different. So when we say about diffraction or developed the theory, so we assumed that each point in the slit we divided into n number of points, and we say each point acts like a source of wave, electromagnetic wave, and then we take the superposition of that. Okay, so that is what basically we do in interference as well. Okay, so you can also then find out what is the condition for maxima and minima, and let's say when I will be equal to 0, this minima, when gamma is equal to, let's say, pi by 2, 3 pi by 2, and so on. Okay, so if gamma is this much, so you'll have intensity will be 0. And also when beta is equal to m pi, when m is not equal to 0. So only except this condition, if beta is m pi, so this term, the sine square beta term will be 0, and intensity is also 0. So there are two conditions for minima. So both have to be satisfied. So you can also calculate this in terms of the angle. Angle is, so now b sine theta, so would be equal to m pi, and so these conditions, so now you are these conditions are for the minima. So this d sine theta would be equal to m plus half lambda. So this is comes from the phase difference that we just said. Beta is equal to m pi, and beta is nothing but lambda by b sine theta. Okay, or b sine theta by lambda, the inverse of that. So b sine theta would be equal to m lambda, and the condition gamma is equal to pi by 2 and 3 pi by 2 leads to this condition d sine theta equal to m plus half lambda, which is also we saw in case of interference pattern. And similarly, maxima we would observe when gamma is equal to 2 and 5. Okay. And anyway, for the central one, there is no change. Central one will always be when m is equal to 0, and that will be 4i square. That is the central intensity. So now if you take instead of 2 such slits, so now if you take n such slits, okay, so each has a width b and distance, let's say we say it is d. So what we have is n slit diffraction from n slits. So this is known as nothing but a you have a grating here. So you have created a grating. So this is a diffraction grating you have created, which has n slits. N can be really large. And now you can extend the theory from one slit to two slits to n number of slits. In that case, your electric field will be, so again, sine beta by beta. So it will be cos omega t minus beta. So for the first slit, this is cos omega t minus beta. For the second slit, it will be minus beta minus phi 1. And for the nth slit, it will be minus beta minus n minus 1 phi. So now if you again simplify this trigonometric function, so you will obtain a relation sine n gamma by sine gamma into cosine omega t minus beta minus half n minus 1 phi 1. Okay, so this is your amplitude of the resultant field due to the superposition of electric field that comes from n number of slits. Okay, so you can see again the intensity. So gamma is again defined by this d lambda, sorry, pi lambda d sine theta, like before. And the intensity again you can write as I naught sine square beta by beta square and sine square n gamma by sine square gamma. So this is again similar to a single slit. This intensity distribution is due to a single slit, and this is due to your interference of n slits. So both the things are happening here. So you have a diffraction from each single slit, which is given by this factor, the intensity, and this one tells you the intensity distribution due to the interference between the slits. Now, if you take this for large n, your maxima would be, let's look at this again. So for large n, maxima is when gamma is equal to m pi. Okay, so what it means, gamma is m pi, and m should not be equal to 0 again. And this gamma equal to m pi means your pi d sine theta by lambda equal to m pi, and your d sine theta is equal to m lambda. So this is known as your grating equation. I think probably you already know that. So this is the grating equation. And when gamma is equal to m pi, so your intensity will be nothing but m square I naught sine square beta by beta square. Because in the limit when gamma goes to m pi, sine square, so this term sine square n gamma by sine square gamma will be nothing but plus minus n. So this is your intensity maxima. So the central one will have maximum intensity n square I naught. Okay, so that means now you have increased the intensity, and what it means, so you don't have only one maxima. The best thing what happens is you will have several maxima corresponding to when beta is so beta is defined like this, right? So just to remember again, and your sine, so substituting that, so if sine theta is m lambda by d, okay, so in that case your beta would be equal to pi b m, or beta is equal to pi b, or d sine theta is m lambda, and then beta is equal to this much. So you will always have a intensity n square I naught. Okay, and these are known as your principal maximum. So you will have a principal maxima and then your minima, and then some secondary maxima as well. So each, so let show me, I'll show the, yes. So this is how the plot would look like. So when you plot the sine square n gamma by sine square gamma as a function of now angle theta, so pi, 2 pi, and so on for different n values. So this n equal to 5. So what you see is a central, a principal maxima. Then you have a diffraction pattern around that. And so you also have secondary maxima. So these are your secondary maxima. And this is your principal. All these are principal maxima, which corresponds to this theta when they are equal to 0 or pi, m pi, okay, basically. And the correspondingly the minima would be intensity when it will be 0. The condition would be when b sine theta is equal to n lambda, or n gamma is so let's first explore. Okay, so this is so n is equal to 5. Now if you increase n equal to 12, so again it's the same situation. What only happened as the intensity has increased of the central peak, because there is a n square term. Okay, so that's why the intensity is much higher in this case, but you have the features are very similar. So you have this principal maximum and then secondary maxima and the minima. So this is a really nice thing about this grating, that you can actually create this many such maxima, and what is the condition for minima? So minima or intensity will be 0 when your b sine theta is equal to n lambda, or n equal to 1, 2, 3, and so on. Because in that case, your beta is n pi, and yeah, so that will lead to 0 intensity. So sine square beta by beta square term will vanish. So n is not equal to 0. So except that, so n is equal to 1, 2, 3. So in that case, sine beta will be 0, and your intensity will be 0. So another condition also lead to a minima is when you look at, because you have two contributions to the intensity, right? So one is due to the diffraction one and due to the interference one. So the interference part will make sure that intensity will be 0 when n gamma is equal to p into pi. Okay, and p should not be equal to n, 2n, and so on. So if p is equal to n, in that case you have a principal maximum. So if n gamma is equal to, let's say, p prime pi, and I say p prime is equal to n, 2n, and so on, so that would correspond to a principal maximum that we saw earlier. Okay. So when you look at the path difference, so d sine theta we said is equal to m lambda, right? That is the condition, the grating equation that we derived. And the path difference you can write something like lambda by uh, lambda by n, and some multiple of, oh no, so lambda by n, okay, and some integer multiple. Okay, so this is your path difference. Okay, lambda n by p, or you basically write this as m lambda. So you can write it like lambda p by n, so p at certain value. So now if you look at this condition for maxima and minima, so we can write down, so when d sine theta is equal to, let's say p is equal to 1, so lambda by n, that will be a minima. 2 lambda by n, that is also a lambda, a minima. And then you go to n minus 1 by n lambda, that is a minima. But now when n is equal to n, or p is equal to n, so that is a, so you have a maxima here. So these are all minima, right? So these are all, so the angle where you have the minima is appearing. So this is lambda by n, 2 lambda by n, n minus 1 by n lambda. But whenever n is equal to n, the capital N, or P, the P is equal to capital N, immediately you have a principal maxima. And then after that, again, you have the minima, which is given by n plus 1 by n lambda, then n plus 2 by n lambda, and so on, which will go up to 2n minus 1 by n lambda. Okay, and then when n is equal to, or p is equal to 2n, so you will have a principal maxima again. Okay, so this is
Excuse
how this, yes.
Sir, what is this difference between maxima and principal maxima by
So
geometry?
yes, principal maxima you see here. So this is your principal maxima, where the intensity is n square into your I naught square, I naught. N square term is there. But there will be also, so each slit now acts as so you can say each slit, you will see a diffraction pattern due to each slit. So this is what a diffraction pattern of one slit, let's say, looks like. And this is what this intensity, the principal, the central maximum you see. And then you have also some additional peaks here. So for example, here, this is also a maximum, but they are not a primary or principal maximum. They are the secondary maximum, and they appear because of the diffraction, because you have a single slit diffraction. But now, since you have n slits and you have an interference pattern, so you have again you have an interference pattern with bright fringe here. So in a double slit, what you would expect, you have a bright fringe here, and then in between there is no fringe. Okay, so dark fringe. But since this is an N slit, it's a diffraction is there, so you have some of these features in between that. Okay, so
Yes,
this is what the secondary maxima are. Okay.
sir, means principal maxima is same as central maxima.
Yes. All these principal maxima will have the same intensity. So just like in an interference pattern, so you'd expect that all bright fringes will have equal intensity.
Yes, sir. Thank you, sir.
Yeah. So so this is how it goes on. And what you would observe, one thing, that between two principal maxima, so you have, so if this is my, let's go back here. So if I have these two principal maxima, so I have n minus 1 minima in between two principal maxima. Okay, so this is always happens in a diffraction grating. So you have two n minus 1 minima between. So if so this is 0. This is nth n is equal to 1. Okay. So this is n is equal to, let's say, 0, n equal to 1. I mean, you should not say like that, because n is 12 means all these. So you observe. So let's say 12 such maxima, but within each principal maxima, so you will have. So yeah, in this case, let's say 12 minus 1, so you'll observe 11 minima within two principal maxima. Okay, so here you'll have 11 minima. So here you'll have also 11 minima, and so on. So if your n is now 5, so here you'll observe 5 minus 1. So I don't know why they have put, oh yeah, so you can see that here, no? So you have 1 minima here, 1, 2, 3, 4. Okay, so n is equal to 5. So you have 4 minima here. Right? So this is what you will always observe in a diffraction grating. So sometimes you will also have some missing order in the diffraction grating. So the missing order will observe when both your condition for interference and so interference condition leads to a destructive one, and the minima of diffraction also is satisfied. So that would happen only when you have these two conditions are satisfied simultaneously. So B sine theta is also equal to let's say n lambda, and n is not equal to 0. So if both the conditions are satisfied simultaneously, you will observe some missing peaks actually. Okay, so this diffraction grating is useful when we talk about for example, this eddy pattern that we discussed is useful when we talk about the resolving power of like you want to resolve some objects. So in telescope or in microscope. So I think that you already know about the Rayleigh criterion, which is for a telescope, it's like 1.22 lambda. So delta theta is equal to 1.22 lambda by d, where d is your numerical aperture or the size of your lens. Okay, so that's why if you take so that means if you want to resolve two objects nicely which are far away, for example stars, using a telescope, so you would like to use a objective lens with high large d, so large aperture. If d is large, so in that case your resolving power is high, so you can actually distinguish between the two distant stars. So similarly, you can also differentiate between two objects in a microscope. Again, they will satisfy the same condition here, and this condition comes from you assuming that each object behaves like a point source, which leads to a airy disk. Okay, so airy disk pattern, and you say you will just resolve when the maximum of one airy disk lies at the minima of the second airy disk. So I think you are aware of this, right? This is the Rayleigh criterion, and what is the, so just go through that, revisit it, and this comes from this diffraction theory. So another very interesting application, not application, but how it is useful, this diffraction theory is useful in other fields. I will demonstrate that. When we talk about crystals, so when we talk about solids, so any material is made up of atoms. Okay, so and the atoms are, oh yeah, okay, before that I wanted to show you a situation. Yes. So here we have a grating. So grating, I think you can define a grating if you so normally you have to know the what is the grating element. Grating element is your so normally you say, let's say you have 15,000 lines per inch. So in that case, the grating element would be D will be so 1 inch by 15,000. So which is, let's say, 2.54 centimeter by 15,000. So this is the distance between your two adjacent slits in a grating. And this 15,000 is basically the source, how large is the n. So n value, the larger, the higher is the resolution of your grating. And this grating, the spectrum that comes from a grating also depends on how you illuminate it. So for example, if you illuminate with a circular aperture like a pinhole, so you'll observe a pattern something like this on the screen. But if you use a slit this to illuminate your grating, so you will observe this kind of pattern on the screen. Okay, so it also reflects how you illuminate the grating. That also plays a role in the spectrum of grating. Okay, so we will see one example of this how useful it is in the other field. So let's say if I take a crystal, okay, so what is a crystal? So crystal is nothing but a regular arrangement of atoms. Okay, so what we are talking about is X-ray diffraction. So so earlier what we saw is a diffraction pattern due to optical light, where we have grating and so on. And if you take a solid which is made up of many atoms, so the atoms are regularly arranged there. So what it means that you can define a small volume which is known as the unit cell. Okay, and this unit cell uh, describes the arrangement of atom of the crystal. And now if you repeat this unit cell, you will create the crystal. Okay, so this is what a crystal or any solid or a crystalline solid is made up of. So it is made up of atoms which are a regular arrangement. And since this arrangement is regular or periodic, so what you can do is you can define a small volume which we call the unit cell. And this unit cell, if you repeat this unit cell, you will create the crystal. And this unit cell basically tells you how the atoms are arranged in a unit cell. Okay, and this arrangement is a you just repeat in all direction, all three directions, and you create the three-dimensional crystal. So now this the separation, the distance between the atoms is typically of the order of the wavelength of X-rays. So this is that means these crystals act as a natural grating for your X-rays. So if you go to your X-rays, which is let's say the wavelength is of the order of 1 angstrom, about 1 angstrom. So for copper it is 1.54 angstrom. So if you do that, use that, and you see the atomic distances, the interatomic distances. So they are of the order of this angstrom, and you will observe this diffraction, and this acts as a natural grating for X-rays. So this is a unit cell. This is defined here. So what you have is, yeah, this is a sodium chloride crystal. So which is the common salt that you use, NaCl. So the black ones are your chlorine. This is your chlorine, and this is your sodium atoms, or and you see they are arranged in a very regular manner. And what more you can also observe that, so this is a cubic, so we call it a cubic crystal. Okay. And your cubic crystal can have three different configuration. One is a simple cubic, okay, and another is a body center cubic or BCC, and another is face center cubic, FCC. So three different ways how a cubic crystal you can find the arrangement of atoms. So if I draw that FCC or simple cubic, so this is a simple cubic structure. What I have is atoms in the each corner. Okay, so this is my simple cubic. Now what is a body centered cubic? So again I take a crystal. Oh, sorry. So I have atoms here, here in each corner, and then in the body center. So this is a three-dimensional picture. So at the body center, I will have another atom. So this is my BCC, and FCC will be in the face center. So if you have a crystal like this, again, atoms here in the corner. Oh, come on. Here, 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 here. And then I will have also atoms in the faces, each face. So I have 6 faces, 1, 2, 3, 4, then top 5, bottom 6. So on the 6 faces, I will have also atoms. So this is my FCC structure. So this is how atoms in a cubic crystal can be arranged. So there can be other kind of crystal structure as well, like hexagonal or pyramidal, or many other possibilities are there. And one thing what you can already observe that these atoms actually, when we talk about this diffraction of X-rays, so we don't talk about the only the interatomic distance, but rather we talk something about the interplanar distance. So what is interplanar here? So when we say this plane here, so we have this one plane here, and this is another plane. So they are like a parallel set of planes. So when I repeat this unit cell further, so I will have this set of parallel planes which act like a, now my N slits actually. So this is acting like a N slit that I discussed earlier. So I can say, like, if I have a plane, maybe I have a picture here. Yes. So what you see here is an atomic plane here. This top one, this is an atomic plane. This is another atomic plane. And what you have is a distance d between these atomic planes. And this d is your interplanar distance. So this is the distance between two atomic planes, and they will act like a grating now, and that is what they will diffract. And what is the condition for the diffraction? So again, it is the same condition that we always this grating. So it will be again the same grating condition. So which is, so instead of d sine theta equal to m lambda, it will be 2d sine theta will be equal to m lambda. So this is the condition for your to obtain intensity maximum. So this grating, this equation is d sine theta m lambda. And what is d? D is like you define for each plane of the atom HKL, where HKL known as the Miller indices. Okay, and they define the atomic plane. So each plane will have a certain index. So you can index each plane using this Miller indices HKL, the value HKL, and you can also find out what is the value of HKL by finding out what is the intersect of the plane with your Cartesian coordinates, the axis. Okay, so here, let's say if I take this cubic crystal, so if I define my coordinate like this, and now I am looking at, let's say, this plane here, okay, one face of the cube. So I can calculate this. This is normally we'll call a 1, 0, 0. So this is, let's say, x, y, z. So it so this plane is this is a xz plane. Okay, so it's in the xz plane and cuts y at infinite. Okay, so you call it. So we will talk about that in the next class because there is not enough time for today. But what I want to emphasize here, so you can use these crystals as a natural grating, and then you can also use X-rays to look at the structure, and you can find out so you will have a peak corresponding to when the grating condition is satisfied, which is known as this 2D sine theta m lambda, which is known as the Bragg's law. Okay. Why we have a factor of 2D? Because if you look at the wave front here, that is getting diffracted. So W1, W2 is the incident wave front, and theta is the angle of incidence. This is theta, angle of incidence. Now, so when you look at the phase or the path difference between, let's say, a wave that comes from this plane, this atom, and the wave that comes from this atom, okay, what is the path difference? So the path difference is, so now if I draw a perpendicular, so I have drawn a perpendicular line here and another perpendicular line here. So this B1x and B1y is the extra path that the wave will travel when it is diffracted from B1 compared to atom B. So this is from the top surface like this, but the bottom surface will have an additional path difference, xb1 and yb1. So this is the path difference, xb1 plus yb1. And how much is the path difference? If this is d, so this is d and this is theta, so this xb1 will be d sine theta and yb1 will be also d sine theta. So d sine theta plus d sine theta, so which tells you this is equal to 2d sine theta. And then if this path difference is integral multiple of lambda, so you will have a constructive interference, and that is when you will observe a peak due to the diffraction. So these two waves basically, so there is a diffraction and these two waves, they will now constructively interfere if this condition is satisfied, and you will obtain a peak. Okay, so this is your Bragg's law.
Sir, quiz कितने बजे से?
Sorry?
Sir, when is our quiz?
Quiz we will start at 12:50.
Okay, sir. Sir, do we have to join the class and give quiz, or we can leave the class?
No, you have to join.
So means we need to stay in this class only
Yes,
at the time of
yes,
quiz.
stay here. Yes.
Okay, sir.
Yeah, I think I'll stop now. So I'll give. So we'll start in 5 minutes. If you have any question.
Sir, 7 मिनट का quiz, sir, इतने कम time.
Yeah, it is not much actually. Not there's not many
Yes.
questions. Okay.
So you should have increased the time.
Yes, sir. At
Yes,
least
sir.
10 minutes.
The
Sir,
No,
ten.
there are
sir,
not many
maybe
questions.
10 minutes, sir. Maybe 10
Yes,
minutes.
sir.
Sometime our network is weak. We are not registered.
नेट इशू भी होगा तो भी 10
So
मिनट
it
में
takes
लगेगा.
only 2 minutes to
Yes,
open
sir.
the form and submit it. So
Sir, just increase
Yes,
it to
sir.
10
No, there is
minutes.
not enough, not many questions. So we will see.
How
It
many
will
questions
take
are
a
there?
minute.
Sir, at
Then
least 3
filling
minutes
names
for
and all
submission.
it will take
Sir,
1 minute.
No, no, I
sir,
am.
we understand.
I am.
That
Listen,
So
this
7
is
minutes
this
of
is
time and
the
that is.
Sir, at least submission time.
Yes, sir.
the
Yes, sir.
format I am following. I will keep like that. So I will not.
Sir,
Sir, if
It
our
will take a
submission
minute.
are
It
at
will
10
take a
So
minute.
seconds
whatever
or
you
20
can,
seconds.
how much you can do, you can solve. So
sir, can you give us 1 or 2 minutes extra for submission?
no, no, no. So it will be really strictly follow. So don't try to submit late.
If there is 1 minute late sir, अगर मान लीजिए सर सबमिशन नहीं हो
No,
पाया
no, I will not consider. I will not
sir,
consider.
excuse me,
Sir,
sir.
but there are also network issues.
sir.
Google form. So that's why
So we have to
it's 7
submit
minutes.
before like 12:57 or 12:50, like till the end of 12:59, like 12:57 59 second, 12:57 and 59, or at
So look,
12:56.
I will check. I mean, if the Google the submission says it is done late, so it is done late. So I cannot say whether it is 57, 57.1, or 57.2. Okay,
How many questions are there?
you will see that when you open the Google form.
And like, will we have a best of one? Like, we're giving two optics quiz, right? So, like, is there a way
No,
that
no, no. Both will be
both will be
considered.
considered?
Yes. So I will
Sir, if the
assign it at 12.
submission are if the submission is 2 second or 3 second late, would it be considered?
So
I
what
guess
can you
you
do in
can
2 seconds,
consider
three
up to 1
seconds?
minute.
Let
No,
me.
no. If we click
You
on
think
557,
2 seconds is
sometimes the Google form gets submitted 5 second late. If we click on 557 exactly, it gets
Mhm.
submitted at 2 seconds. It has a delay of 2 or 3 seconds.
Yeah, that I
Yes,
will
sir.
look at it.
Many of the
So
quiz.
don't worry about that. So you try to submit it on time. So that is what matters. So if you say I will submit at 1 o'clock, so definitely it will not be considered. So you have to try to submit at 12:57. So then if it is done from your side, so that is fine.
So if we submit at exactly 57, then it will be considered or not?
Can we leave the meet?
I told, I mean, if Google says it is done late, I will assume it is done late. That's all.
Sir, in that short time, we do have to consider how many seconds, right? Like 57 and how many seconds?
Look, I mean, I just told you. So I am following a format which I have followed for like last
57 से
2
पहले
years.
करना है.
Yes,
So
you
when
have
will
to
you
submit
post it?
before 57. That's all. So don't wait for the last minute.
When will you post the quiz? 48.
तो 7 मिनट की क्विज है उसमें भी सर लास्ट मिनट तक नहीं जाएंगे तो सर टाइम ही कहाँ मिलेगा.
What?
Can you tell us something about NSEM paper pattern and all?
NSEM is no, I think better you concentrate now for the quiz. So I will
Yes, sir.
tell
1
you
minute.
about NSEM about tomorrow. Okay.
Sir, would you be sharing it in Google Classroom or in the chat? The link
What?
to the Google, the link to the Google form.
Sir, should we
Google
leave
form
the
will
meet?
be in the Google Classroom, so you'll be updated. So go to Google Classroom, but stay in the Google Meet here. But open your classroom and then you will see the assignment.
Hello.
Yes.
Sir, where is the quiz appears? In the classroom or
It
the
appears.
chat?
It's already in the classroom. In the classroom.
Sir, is this multiple choice?
Yes, yes.
knockdown seconds to skip the ad, right? I get it. But what if you never had to watch an ad again? What if you had a browser that actually respected your privacy? Well, Brave browser does. And you can import your bookmarks too. Download Brave today and see all the hype about it. It's free.
When I was a student, I write long essays that I'd work on for days. But now I'm writing short emails and messages all day, every day.
So submit now, because I will stop accepting any further responses.
Sir, in a lot of
Yes.
in a lot of my questions, it is showing correct, but I've not gotten marks for it.
Yes,
Yes.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
You have
Yes, sir.
not marked the right answer in
Like,
that.
yeah, I've got like 5 marks extra, but it's not giving marks.
Yes, sir.
What do you mean by that?
मतलब आंसर सही है पर मार्क्स नहीं दिए.
Yes, sir.
Yes, sir.
आप एक से ज्यादा करेक्ट होगा.
Excuse me, sir.
Yes, sir.
पार्शियल मार्किंग नहीं है सर.
सर ओके क्वेश्चंस में ये भी नहीं बताया कौन सा आंसर सही है.
हाँ सर, आपने सर वो मार्क नहीं किया है कि आंसर करेक्ट कौन सा है, तो क्विज जो है ना सर वो कैलकुलेट नहीं कर रहा
मेरे भी
कि
4
आपके
और आ
आंसर
रहे.
सही कि नहीं.
अरे कंत.
नहीं वो मल्टीपल करेक्ट है ना, तो उसमें दो एक और ऑप्शन हो रहेगा, मतलब तुमने दो ही सही किए होंगे.
यस सर, वो मल्टीपल है इसलिए गलत हो
It's showing I've done all the right answers. Still,
No, if you have
एक
all the right answers, then you will get full mark. Otherwise, so there is no step marking or anything. So either you get 0 or full.
So can you discuss the answers, sir?
I will share the answers
No, sir, in one question.
classroom. Okay. I will share the answers in the Google Classroom. Yes.
Excuse me, sir.
Yes.
So, could you possibly reschedule tomorrow's quiz and keep it on Saturday evening, maybe?
I mean, I can keep. So you discuss
Yes,
with
sir.
the class, and if everyone is comfortable with Saturday, I will do that. No problem.
Okay, we'll discuss that, but most probably Saturday evening is free for all of us.
Okay, no problem. I mean, I will be. I can do
Sir,
that.
because tomorrow we have 2 quizzes.
Okay.
And also, sir, can you please share the solutions of this one?
Yes, I will share. Yeah.
Sir, actually there is a question related to refractive index of homogeneous medium. In that I choose the correct option, still it shows that the answer
There
is
can
wrong.
be more options can be
Yes,
correct.
sir. The first question, I think all options are correct because travels in any matlab, how to travel, it's not important.
But they are talking about the change of refractive index.
Sir,
Yes.
sir, there's this question: which of the following sources will reduce interference pattern in Young's double slit
yes,
experiment?
yes.
Sir, my both the answers are correct, yet I got 0, sir.
Yes.
Sir, see.
Yes.
अरे हाँ देखा.
Yes, sir.
We've got the
Sir, yes.
Sir, it is because 3 answers are correct, sir.
What
answers were
are
correct?
the answers are
What
correct?
is Sachin correct?
3 answers are correct.
So wait a minute.
and I got marks.
Listen. So I will share the answers. So then you compare, and then you will know whether your answers are correct or not. Okay. So now, if you discuss like this, so I cannot say particularly because it will be difficult immediately to check whether which one is your response and so on. Okay, because there are already like 240 responses. So I would suggest.
So there is a question.
I will share the solution. You check, and then if you think it is wrong, you tell me. Okay.
Sir, we can mail you in that case.
Yes, you can make it.
Okay, fine, thank you.
So excuse me, sir. So there is a question to find the intrinsic impedance of the glass, where the impedance of free space is 120. So if we find like you said that n upon n free space is equal to 1 upon n, that is 1 upon the refractive index. So the answer must be 80 pi ohm but there is no option like 80 ohm.
80 pi, yes.
Yes, sir. It should be 85.
85.
Yes, sir.
Actually, yes,
Yes,
Yes.
sir.
Eight
No
only. Yes, sir.
yes, sir, not
It's
80.
showing eight.
चलो
Eight's
सर
correct option.
सर
It is
मेरा
showing.
सर वाईफाई ऑफ हो गया था सर, अभी सबमिट नहीं दे रहा सर। 57 मैंने सबमिट किया था।
No, I will not consider that kind of excuses right now. So
सर सच में वाईफाई सर ऑफ हो गया था सर। सर प्लीज सर सबमिट मैंने सर 57 में ही किया था, अभी सर ले ही नहीं रहा।
no, because I have stopped accepting any responses right now.
सर मैंने 57 में ही किया था, प्लीज सर। सर मैंने सर 57 में स्टार्ट किया सर, ले ही नहीं रहा था, तो मैं क्या करूँ सर। वाईफाई सर अचानक ऑफ हो गया था। प्लीज सर। हेलो।
So I will share the solutions, and then you will see whether your answers are correct or not. Okay. And then we will. So if you have any issues, so you will then mail me. So now we can stop, and then we'll meet again tomorrow.
सर मैं फॉर्म सब फिलअप है सर, बस एक्सेप्ट कर लीजिए ना प्लीज सर।